is a wave function? Look here, the definition of wave function is, a wave function is a quantity that will give the wave-like property associated with a moving particle. And it is going to be a function of space and time and is generally denoted by psi of xt. It is also called as the state function, and this wave function is obtained by solving a fundamental equation in quantum mechanics, which we call it as Schrodinger's wave equation. Now, what is wave equation? Therefore, look here. A wave equation, a wave function is a quantity that gives the wave-like property associated with a moving particle. It is going to be a function of space and time, and it is denoted by psi of xt. It is also called as state function. This function is obtained by solving fundamental equation in quantum mechanics, which we call it as Schrodinger's wave equation. Okay, what does this mean? Okay, again, everything is related to the matter wave that is associated with a moving particle. So therefore, let us look at the profile of. If I move forward, yeah, this is matter wave, correct? So it is an amplitude modulated wave. Okay, yeah. Now can you see here? See this matter wave, it can spread in space. It can shrink. Okay, the matter wave can spread or it can shrink. Okay, so therefore, what is a matter wave? Okay, look here. Once again, I will just demonstrate. The matter wave can either expand or it can shrink. Okay, that is the de Broglie wavelength can increase or it can decrease. So de Broglie wavelength can vary with the time. Okay, because it depends on how the particle moves in a given medium. Okay, therefore the matter wave can either increase or decrease. The wavelength can increase or decrease. Therefore, it is going to be a function of space and time. Okay, so I think now I will look at this. Look here. Suppose this is a matter wave. Yeah, suppose I use red color. See, suppose I fit a coordinate system to this. Fit a coordinate system to this. This is y-axis and this is going to be the x-axis. Okay, this length, suppose I denote it as de Broglie wavelength, or for example lambda 1. Okay, can you see from this figure that as time lapses, what will happen? The de Broglie wavelength can either increase or it can decrease. De Broglie wavelength can either increase or it can decrease. Okay, de Broglie wavelength can either increase or decrease. Okay, either it can increase or decrease. It can increase or decrease. Okay, so therefore, what is a wave function? A wave function is a quantity that gives the wave-like property associated with a moving particle. It is going to be a function of space and time. Can you see here? This matter wave is spread in space. Therefore, it is going to be a function of space. Next, what happens as time lapses? As time lapses, the matter wave can either increase or it can shrink. It can either increase or shrink. So therefore, it is going to be a function of both space and time. So it is denoted by psi of x comma t. It is also called as the state function. So this is obtained by solving a fundamental equation, which we call it as Schrodinger's wave equation. Okay, so anyone has any doubts related to the definition of wave function? So what is a wave function? A wave function is related with the de Broglie wave. So it is an amplitude modulated wave that we already know. The de Broglie wave, as time lapses, what will happen? Either it can increase, the de Broglie wavelength can increase or it can shrink. It can either increase or decrease. Therefore, the de Broglie wavelength is going to be a function of space and time, which we call it as wave function. Okay? Manji Gowda, today also you are raising hands, man. I think we'll move on. Yeah. Okay. So I think the definition of wave function is done. Okay. Next we will discuss the importance of wave function, which we call it as physical significance of wave function. Okay. What does the wave function give us? What does the wave function give us? Look here. What is the physical significance of wave function? Yeah. This is the physical significance of wave function. See, suppose I place it here. Okay. Yes, Pa. Okay. Now, what is the physical significance of wave function? Look here. The physical significance of wave function. This is also called as the Max-Born's interpretation of wave function. It's also called, yeah. So this is also called as the Max-Born's interpretation of wave function. Okay. Now, what is the significance of wave function is? Okay. Look here. So, according to Heisenberg uncertainty principle, can we tell that you can find electron precisely in this region? Answer is no. Okay, you can't talk about exact value of location of an electron or exact value of the velocity of an electron. All you can talk is whether the given value is going to be of greater chance or lesser chance. Therefore, likewise, look here. Now, what is the Max-Born's interpretation of wave function? The Max-Born's interpretation of wave function is, it gives us the probability of finding a particle is more in that region where the amplitude of the wave function is high. The probability of finding a particle in a given region X is given by simply taking the wave function and squaring it. Okay. Therefore, take the wave function and if you square it, that will give us the probability of finding the particle at a given point X. Okay. So therefore, what does that mean? What does that mean? Okay. Look here. Let me take again the same example. I'll take this matter wave. Okay. So can you see from this figure? See, for example, if I take say brown color. Yeah, brown color. See, for example, in this figure, you can see that the amplitude is high in this region. Okay. These are the two regions where the amplitude is high. Okay. See, for example, this amplitude. Say, for example, this is 10 watts. Say, for example, this is 80 watts. What will this be? This will be, for example, 60 watts. What is this? For example, 40 watts. This is 20 watts. And this is roughly 2 watts. So, what are the numbers did I take? 80, 60, 40, then say 20 and 3. Okay. So what are these? These are nothing but it is the height of that is the amplitude of the wave. Okay. Once again, look here. See, for example, if I see in this example, can you see here? This height is around 80 watts. This is 60 watts. This is 40 watts. This is 20 watts. And this is around 3 watts. Okay. So can you see here from this figure? So there is since the amplitude is high here, there is a greater chance of finding the particle in this region. Okay. There is a greater chance of finding the particle in this region. Okay. Can you see here? So therefore, what is the amplitude of the wave function give you? Look here, this is simply analogous to the fact that the energy of the wave is proportional to square of amplitude. Square of amplitude. So take the amplitude of the wave function at the point X. If you square it, that will give us the probability of finding the particle. Okay. Therefore, look here in this example. For example, there is a greater, for example, there is a 80% chance of finding an electron here, and there is some 40% of chance of finding electron here, and here some 15%, here 10%, here it is almost 1%. Okay, can you see here? What is the chance of finding the particle? The chance of finding the particle is So if the amplitude is very high, there is greater chance of finding the particle. So in this example, where is greater chance of finding the particle? The greater chance of finding the particle is in this spot because the amplitude of the wave function is high. Okay, so therefore, what is Max-Born's interpretation of wave function? You take a wave function, look at its height. If you square, that will give you the chances of finding the particle. Therefore, in this example, there is a greater chance of finding the particle roughly in the middle of the wave function, middle of the wave packet. Look here. So what is this distance? This distance is half the wavelength, half the de Broglie wavelength. Therefore, there is greater chance of finding the particle near the middle of the wave packet. Okay. What is the chance of finding the particle here? It is almost zero. What is the chance of finding the particle here? It is almost zero. Okay. Why it is zero here and here? Because the amplitude is roughly zero. Okay. Is this clear? Now what is Max-Born's interpretation of wave function? The Max-Born's interpretation of wave function is, if I choose an arbitrary point x, find the height of the wave function there, square it, that will give you the probability of finding the particle. Okay, got my point? If I choose an arbitrary point x, find the height of the wave function at that point, and if you square it, that will give you the probability of finding the particle. Therefore, in this example, since the amplitude is more in these two regions, there is a greater chance of finding the particle in the middle of the wave function, and you cannot find the particle at this location and at this location at the extreme endpoint because the amplitude is zero. Okay, this much is clear to you all? Any doubts? So what is the importance of wave function? It gives you the probability of finding the particle in a given region, and the probability is more in that region where the amplitude of the wave function is high. Okay, this is similar to the fact that the energy is more in that wave where the amplitude is high. Okay, I think this is done. Next we will move on to a concept called as normalization condition. So what is normalization condition mean? Yeah, again I will take this. Look here. What is normalization condition means? Look here. I think again we will recollect the same thing. Look here. See, consider that you have forgotten your mobile in your study room. Now, if you know for sure that your mobile is somewhere within your study room, what you are going to do? You are going to thoroughly scan or search your study room in order to trace it. Correct? So, likewise, if we know for sure that the particle exists somewhere within this region, okay? For example, if I take the wave function, look here, this is the matter. Yeah, can you see here? See? Now, what is normalization of wave function means? Look here. What is normalization of wave function means? Look here. See, if we know for sure that the particle exists somewhere in a particular region or space, then summing all the probabilities of finding the particle over that region of interest, that will be equal to 1. This is called as normalization of wave function, and it is given by this mathematical expression. Okay, let us again once again recollect read what is normalization of wave function mean. Okay, what is normalization of wave function? Look here. If we know for sure that the particle exists somewhere in a particular region, then adding all the probabilities of finding the particle over that region, that probability, that sum should be equal to 1. And this we call it as normalization of wave function, and it is given by integral of this equal to 1. Okay, what does that mean? Okay, look here. See for example, if I know that the particle exists somewhere within this region, suppose I call this distance as lambda 1. Okay, look here, this is an x-axis. Okay, this is x-axis. This is x-axis. Okay, now if I know for sure that the particle, that an electron exists somewhere within this region, that is between x lying between 0 and lambda 1, this is origin O. Okay, if I know for sure that the particle exists somewhere within this region, if I know for sure that the particle or mobile exists somewhere within this region. Okay, now what I have to do? So look here, for example, here at this point there may be 20% of chance of finding an electron. Here you may have 25% of chance of finding an electron. Here there may be 45% of chance of finding an electron, and so on. Okay, so once again I'll repeat. Look here. See here, in this region there may be some 15% of chance of finding an electron. In this region there may be some 20% of chance of finding an electron. In this region there may be some 25 or 45% of finding an electron, because the amplitude is increasing. Okay, so therefore if I know for sure that the electron exists somewhere within this region, if I add all these probabilities between 0 to lambda 1, the sum of all that probability should be equal to 1. This we call it as what? Normalization condition. So what is the expression for normalization condition? This is the expression. So what is that? See, you take the, what is normalization condition? This is the normalization condition. Okay, what is this? This is normalization condition. What does this mean? Keep your camera at a distance x. Okay, I'm keeping my camera at a distance x. For example, if I use say black color. Okay, look here, for example, my camera is located black color. Okay, my camera is located at the point, this point x. Okay, where is the camera located? Camera is located at the point x. Okay, so where is my camera? Camera is located at the point x. Okay, now what I'll do? Find the height at that point and square it. That is given by modulus of psi of x square. Okay, that is given by modulus of psi of square. Okay, the probability of finding the particle is modulus of psi of x square. Next, what we do? Scan this camera from 0 to lambda 1, and if you add all these probabilities, what does this integral sign mean? Integral sign refers to the fact that I am scanning. Okay, what is this integral sign means? Integral sign refers to the fact that I am scanning my camera from 0 to lambda 1, and the sum of all that probabilities, that should be equal to 1, because I know for sure that my cell phone is there only in this steady room. Okay, so this condition we call it as what? Addition of all these probabilities, that should be equal to 1. This condition we call it as what? Normalization condition. Okay, this is clear. Next, last part, we will look at the properties of acceptable wave function. So what are the four properties of acceptable wave function? Look here. A wave function is a function of space and time. Therefore, the properties of acceptable wave function are: the wave function must be single valued everywhere, the wave function must be finite everywhere, the wave function must be continuous, then its derivative d psi by dx must also be continuous everywhere. Further, if the energy is finite, then the wave function must vanish at infinity. So what are the four properties of wave function? The four properties of wave function are: the wave function must take only one value in our region of interest. For example, from 0 to lambda 1. So the wave function must take only one value or single value in our region of interest. The second property is the wave function should take only finite values. Okay. See, for example, tan pi by 2 is infinity. So therefore, values such as tan pi by 2 or tan minus pi by 2, so these all are not permitted. Okay, what is the second property? The second property is the wave function must be finite everywhere. Third property of the wave function is wave function must be continuous everywhere. Also, its derivative, namely d psi by dx, must also be continuous everywhere. Next, the wave function, the it should its value must be 0 at an infinite distance. Okay. So any wave function, any function or any mathematical function that has these four properties, they are called as eigenfunctions. Okay. So what are eigenfunctions? Any mathematical function psi of x that has these four properties are called eigenfunctions. They are called eigenfunctions. Okay, this much is clear. Next, look here, last part of today's discussion. I'll tell what is Schrodinger wave equation is, and then I will stop. Okay, now look here, what is Schrodinger's wave equation? So what is Schrodinger wave equation? Look here, a Schrodinger's wave equation is a second order differential equation. It is similar to Newton's second law of motion. What is Newton's second law of motion? Force is equal to mass into acceleration. So acceleration is what? Acceleration is d square y by d of, or d square psi by d of t square. Correct? No? This we call it as what? Acceleration. So a Schrodinger wave equation is, what is a Schrodinger wave equation? A Schrodinger wave equation is a second order differential equation. It is analogous to Newton's second law of motion. Newton's second law of motion is nothing but what? Force is equal to mass into acceleration. So that is what I have written mathematically here. Okay. So if we solve Newton's second law of motion, we get the information about the position and the velocity of a particle. Similarly, if we solve Schrodinger wave equation, then we get a function called wave function. From this function, lot of properties about the system under consideration can be studied. Okay, so what is, if you solve Newton's second law of motion, what we are going to get? If we solve Newton's second law of motion, we get the information about the location and velocity of the particle. Likewise, if you solve Schrodinger wave equation, which is also a second order differential equation, what you are going to get? We are going to get the wave function, that is psi being a function of x and t. From this, lot of information about the system under consideration can be studied. Okay, this much is clear. Then there are two types of wave functions. Okay, So there are two types of wave functions. Look here, if the wave function depends only on space, then we call this as time independent wave equation. On the other hand, if the wave function depends both on space and time, then this we call it as what? Time dependent wave function. So look here, if the wave function depends both on space and time, then it is called as the wave function depends both on space and time, then it is called as time dependent Schrodinger wave equation. So here can you see the wave function depends both on space and time. So this is time dependent wave function. On the other hand, if the wave function depends only on space but not on time, then this is called as time independent wave equation. So this is time independent wave function, okay, because here the wave function depends only on x but not on time, okay. Therefore, how many types of wave functions are there? So there are two types of wave functions. They are time dependent wave function and time independent wave function. So in the case of time dependent wave function, what happens? The wave function will depend both on space and time. The wave function will depend both on space and time. On the other hand, in the case of time independent wave function, it depends only on space. Okay, I think with this, I will stop here for now.